So here's another big crazy idea in a room full of people with big crazy ideas. So Shell Worlds, which the original paper appeared here, Javis, January 2009, and I believe both of the reviewers are in this room right now. There's my co-author, Ken. Ken, where is Ken? Raise your hand.
We'll be back in a minute.
Okay. Anyway, so we're also talking about CD. So why should the criteria expand? Well, this idea that we're just going to go out there into the cosmos and find a habitable planet, land on it, and just live there. There's a couple of problems with that, notwithstanding the Kepler project. Stephen Dole, in this amazing seminal work, to imagine it's almost 50 years since he wrote this. It's just an outstanding intellectual product. It was originally called Habitable Planets for Man, and then it was reissued, co-authored with Isaac Asimov in hardcover, which I found in a used bookstore for like $5. Amazing. And this is another book, actually, all of you should get if you can find it. Communications with Extraterrestrial Intelligence, edited by Carl Sagan. This was a conference in the Soviet Union in the early 1970s. And some of the attendees, Freeman Dyson, Kardashev, Crick and Watson, Makarian, Makarian objects, Charles Towns, the inventor of the laser, all these amazing people. So go look that up on Amazon or something. All right, so these two books, I don't have a copy of Martin Fogg's work, but the basic idea is, there's probably not too many of these Earth-like planets. And even if there are, they might be occupied. In fact, as we learn more about the universe, it looks like life really wants to emerge and exist, because every time we look in some outlandish niche, we find some bug living there. So when we get to another world, it may be that it's occupied already. And if the occupants are sentient, from the anthropological point of view, we've got to consider our own unhappy history and realize, because of the vastness of time, the bad interaction can go both ways, right? We're top of the pyramid here, Western civilization, as Jared Diamond indicated in Guns, Germs, and Steel, but that doesn't have to go our way next time. And even if the occupants are non-sentient, it's still a moral hazard to go there and introduce aliens into that environment, okay? And even if the system is uninhabited by anything with a brain, the fact is the 23 essential amino acids of which all our proteins are composed, other systems could have made different choices, because there's a lot of possible amino acids out there, which means you would have allergies all the time or just curl up and die just by being in the ecosystem. And the chances are, actually, that would happen. Of all the and it just takes one bad protein to kill you. Okay, here's another thing. This isn't fitting exactly into the screen, but it's why the space hopper riders have it wrong. This is a dome, a dome city on another world, and that's air pressure inside the dome. So 14.7 psi inside, 0 outside. Sorry, Claudio, it's not SI. 101,325 Pascal. Is that all right?
Thank you.
So, the trouble with this glass dome as pictured in fiction is, even for a small radius of 300 meters, and 100 kilopascals inside, you would actually need 4 inches of steel to hold that air. And if you had an actual glass dome, you got no radiation protection. You have day-night temperature cycles, which create alternating stress, which is bad for materials, and you've got heat loss. So forget domes. And imagine taking that dome I showed you, and imagine extending the radius of the dome, making it bigger and bigger, and extend the radius of the dome to the world. I'm sorry for the second order vibration, that's all the coffee I've been drinking. So imagine extending the radius to the world, which is like Galileo, I believe, his old idea, shoot a cannonball, and the radius, that the way it falls is curvature of the Earth, and then you know you're in orbit. So air pressure without a central body, with any balloon that was as large as a world or even a small moon would burst. There's no known material that could hold 1 atmosphere of air pressure in a container that large. That's because stress is a linear function of radius. It's also a function of the pressure inside, but it's a linear function of radius. So you make a big radius, you make a lot of stress. And these, just look at the last column, these are the factors how much stronger the skin material would have to be, how many times stronger than steel to hold air pressure in something the size of these various worlds. I mean, look at where 50 times stronger than steel. I mean, that's unobtainium, all right? For something the size of Earth, you would need a material that could hold, tested out at 240 billion pascals, or 36 million psi. I mean, that's real unobtainium. And even for a world the size of Ceres, okay, this is Earth's moon, so Ceres, sorry, this is Earth's moon, Luna, so Ceres is about this big compared to Luna. And even for something the size of Ceres, you would need 80 kilo kpsi steel, which is pretty good steel, all right? Now, let's say we have a balloon that doesn't have air. It's just a shell, okay, with a central body inside tugging on it. Well, it turns out you need very strong material to do that too, because you have the balloon, but the air pressure is not holding it up. Gravity's going to tug it down. It's going to be like a great big arch, okay? And the bigger the distance of the arch, the more the compressive force per unit area. So even for a real material, if there's no air pressure inside, it will collapse. So now you see, even if there isn't a central body inside, if you make a shell big enough, because for a spherically symmetric system, you can model it as a point mass. For a shell that's big enough, the self-gravity of the shell, for the right kinds of shell, would collapse the shell, even without a central body. So we have a tension problem, and we have a compression problem, right? So you can see the solution. We just arrange it so that tension equals compression, and that the net stress on the shell is 0, and hence shell worlds. And that's Ceres, and that's Luna. And this, well, actually neither of these blue bands is to scale. Let me show you the proper scale. That's not right either. That's about right. If we were to put a shell around Ceres, the Ceres is 1,000 kilometers in diameter, a little bit less. That's a 20 kilometer air blanket and a shell on top of it. And that's approximately to scale. And that thin geometry actually helps us. So, 7 steps to a new world, as opposed to, 12-step program to a new you. So you start with a small body, otherwise useless and unoccupied. You do whatever sculpture you want to do on the first, carve out basins for future oceans. And then with robots, you lay down a carpet, meter thick of Kevlar, another meter of armor plate, and then you start dumping dirt, regolith, on top of that. And when you've dumped the proper amount of dirt, and the amount of dirt you need is determined by the mass of the central body, you start inflating it with, your big tanks of frozen air that you've shipped in for the purpose. And the balloon will rise above the surface, and you just pump in as much air as you want, and the balloon will grow accordingly until, the height gets tall enough and you stop. Then you add heat to melt the ice, light, because the balloon is not transparent, and life. And in spots, you can decrease the thickness of the dirt that's on top of the Kevlar and the steel. Now, you wouldn't want to thin out those things, but you decrease the dirt and you can hang cities off of the ceiling. Somebody off these. Sorry about that.
It has an
Windows. Don't you love it? So here are 3 shell worlds. Now the distance, the diameters of them are to scale. The atmospheres of these are approximately to scale, but actually I couldn't make the blue line thin enough here and have it still show up on screen. The interesting thing about putting a shell around a world is, see this little red line here, and here, and here? And let me use Earth as an example. The deepest mineral mine I know of on Earth is the one up in Sudbury, Ontario, the nickel mine. It's about, what, 2 miles down? When a mine played out, they put the neutrino detector down there. And then there's the Kimberley diamond mines in Africa. They're well over a mile down. So those are the deepest mines I know of. And the deepest oil wells I've ever heard of, I don't believe any of them go below 10 kilometers. So 10 kilometers in the scale of this globe, the Earth is 10,000 kilometers, or well, 12,000 kilometers across. So 10 kilometers is like the thickness of this business card, all right? Which is like nothing. And that is the exploitable volume that we have available to us here on Earth. Now on the moon, we could go quite a bit more. We could go down maybe, 100 kilometers or 200 kilometers before the pressure got to be the problem. But on a little world like Ceres, like this, compared to the moon, on a little world like Ceres, you could go all the way to the core and never have a pressure problem, which means this entire volume is available to be exploited. You want to put this volume in perspective? If you covered all of planet Earth, if there were no, just imagine a world-girdling city packed with the density of Manhattan Island, where every building was a kilometer high, and you covered all 500 million square kilometers of Earth's surface with 1 kilometer high skyscrapers, you would have the same occupied volume that Ceres would provide if it had a shell around it that you could live in and walk around in shirt sleeves. Which is why one of the things that falls out of our work, by having this tremendous amount of volume, usable, exploitable volume with resources available to us, what did you call it? The material basis of the culture? With that kind of material basis, it's possible that the Belt civilization, especially Ceres, could, a few hundred years from now, be the richest locus of the entire solar system. And Earth would be some kind of backwater, where people came from. The old country, sort of like, people, the Irish, I'm Irish, and it's like what we used to say about Ireland, until a few years ago. Actually, we're saying it now, too. Yeah. Thanks to the economic crisis. So that one you've already seen. Okay, well, the bill of materials is pretty substantial. These figures on the right-hand side are in trillions of metric tons. Sounds like a lot. Well, it is a lot by today's standards, but it's definitely doable. But to cover Ceres, the world's Ceres, with a 1 meter layer of iron and another meter of Kevlar, you would need 25 trillion tons of nickel iron. There's asteroids out there that can do the job. And 6 trillion tons of carbon. Now for the dirt, you would need 1 quadrillion metric tons of dirt, but then you would use Ceres' own material for that. I'll skip to the oxygen. Oxygen you can get by cracking dirt. because oxygen, very common material. And to replicate Earth's atmosphere, you'd even use, you need a mere trillion tons of argon. It's practically a rounding error. As for how much water you would need, well, I'll get to that in a minute. But the reason I made this one red, to duplicate that 20-kilometer shell of atmosphere around Ceres, you would need 50 trillion tons of nitrogen. And nitrogen, actually, in the solar system, that's kind of a limiting reagent. There's only one place I know of besides here that has lots of nitrogen, and that's Titan, Saturn's moon Titan. So that would have to be imported. Most of this other stuff you could get locally. And finally, water. This is the point I always, you can't make it too much. How much more do you want? Well, if we want to recreate the Earth, maybe in a smaller scale, that's one view of Earth, right? That's from about 7,000 miles over Tahiti. There's another view of Earth, right? So what do you see? What? So to put a shell around Ceres, you'd need not a very large nickel-iron asteroid. There's hundreds of these, okay? 18-kilometer asteroid and a carbonaceous chondrite of about the same size, all right? And if you were to get the dirt by rendering a stony asteroid into dirt, that's how big the stony asteroid would have to be. However, I did say you could probably just take Ceres soil and just dump it on the shell as you're weaving the shell and laying it down on the surface. But if you were to use an asteroid, that's what you would need. And then finally, when we first wrote this paper, the subsurface ocean on Ceres had not been theorized to exist yet.
or Enceladus?
No, Ceres. It is thought that Ceres might have a 100-kilometer thick ice layer. And the really amazing thing about that is this tiny little pissant world, 1,000 kilometers across, apparently differentiated. Or that's what the Ceres, and we're going to find out in about 2 years when the probe gets there. 2 years, year and a half, we're going to find that out. But it looks like water is really common in the outer system, and we're not going to have a problem finding water. So, but if you were to needed to import the water and the gases, you would need a 60-kilometer comet that you would render for the ices and the gases to make your atmosphere. So that's the bill of materials, or Lunar, Mercury, or taller propositions. Now you think, this guy's talking about trillions of tons. What a nut job, right? Well, okay, let's put these things in perspective, right? And if you take the perspective of time, think about the miracle of compound interest. Because we are all living in a society we're right in the middle of an exponential growth curve. And if you talk to the extropians, there's no top end to that. Now, I don't know how it's going to play out, but I do know I'm living in extraordinary times. So, okay, 1 trillion tons in perspective. Right now, all of human commerce, excepting basic ores and water, the water we pump around, all of human commerce consists of moving 20 billion tons of stuff every year. 20 billion tons. Our economy right now is, worldwide economy is $50 trillion. We spend $3 trillion a year just on petroleum. Now, we're going to be looking 100 years, 200 years from now, we're going to be looking at some gigantic projects that we can get involved in. And they will involve trillions and quadrillions of dollars, and they will involve really astounding sums of mass. Well, it sounds astounding until you look at how we've actually developed. I mean, let's put these things in perspective. We already have a single industry here on Earth that's worth, one industry that's worth trillions of dollars per year, And in fact, petroleum, oil, gas, and coal is more than half of this figure. So it's double that amount of dollars if you add gas and coal in there, and then it's half of that figure. So that's something we already do. These are fixed projects we've already built not too long ago in space. Now there's okay, thank you, and I'm close to the end. I was just talking about this thing in Russia a couple of weeks ago. Went over to the Academy of Sciences to talk about that. This is a Dyson dot. Basically, it's a solar sail with photovoltaics on one side and a maser array on the other. So while you're shading Earth and cooling it down, you beam the energy back and run your grid on it. Not really going to talk about that, but we think building a Dyson dot, which when we build it is going to be the biggest construction project the human race ever got involved in. And by the way, in the scale of this Earth globe here, the Dyson dot, that's what they would actually look like compared to the Earth. Okay, either the size of Texas or possibly the size of the entire West Coast, depending on how much cooling you needed to do. So when we do it by mid-century, we think it'll cost a few $1 trillion. But compared to what we do on the energy industry, I mean, that is not inconceivable. Now, a shell world is a much bigger proposition. We roughly estimate it'll be 3 orders of magnitude harder. And since this is an interstellar workshop, we think by the end of 2200 that a shell world or an interstellar trip to Alpha Centauri in a slow arc, 3% of light speed, a few percent of light speed, would be resource propositions of similar difficulty. Wait 100 more years when the human race gets really rich and gets used to working with really large amounts of energy and can travel near sea, and again, the constant value will be about the same. You just have to wait 100 more years to make it happen. But, one of the startling things to fall out of this research is these aren't impossible. I mean, you don't have to imagine warp drives or anything impractical. I mean, and in terms of the current human economy, it's something you can conceive of. For example, remember the cathedral building binge in Europe? For 300-400 years, people dumped their entire national wealth into 300 or 400 years into this project, which didn't appear to have a direct economic payoff. Let me very briefly talk about stability. We've been going through the math. It's in our papers. Plus, we have a future paper coming out. We've been looking whether it's stable. Yes, it's structured, zeroth order stable. There's 2 independent restoring forces, gravitational and the atmospheric pressure, that make the system stable. And now we're looking at higher order atmospheric pressures. I'll skip over that, Illumination. I think I should just take questions. So why don't I spend the rest of my time doing that? Because, I'll leave you with 2 quotes. That's Konstantin Tsiolkovsky, and that's Robert A. Heinlein. No, one cannot stay in the cradle forever, and the human race is too small and fragile a basket to keep all its eggs. So why expand the criteria? Well, because shell worlds is a possibility to turn worlds that would ordinarily not be habitable into habitations, and the seedy people should think about that. And you can build them anywhere, including around red dwarfs, lots of red dwarfs, and a really advanced civilization might prefer that because it's a way to kind of live off the radar if you're very shy or very paranoid. All right, now I'll take questions. Very good.
I may have 2 questions hidden in one. One you kind of glossed over, the stability, and
Yeah.
is the question I was going to ask.
Okay.
First of all, I really like everything you talked about, and I see how you set the system in equilibrium so that you have the configuration you're talking about.
Yeah.
But it's still the top of the hill, and it seems like it's an unstable equilibrium to perturbations. And of course, the question is, well, how large of a perturbation do you need to pop that bubble, because if the structure can't support against gravity or the atmosphere, you said that the atmosphere is also a restoring force, but that's, you only have, you have force going out, force going in.
So atmospheres have a scale height, right?
Sure.
And actually, it turns out, even on a shell world, the atmospheric pressure across the height won't be constant. It'll be a little bit denser at the bottom than the top.
So you're saying
And this is the source of, yes. This is what, if you displace the shell off-center, so the model we did was for Ceres, 1,000 kilometer shell displaced 20 kilometers off-center, what happens? Well, it turns out that the part that's closest to the world sees a higher pressure because it's near the bottom than the other, and so it'll restore. And gravitationally, there's independent, but the same kind of restoring force. That one, what we did was we took slices, and we looked at the gravitational pull on each of these rings, and the end caps dominate the effect, but the gravity, as long as the world inside is reasonably symmetric, doesn't have huge mass cons and mountains over 20 kilometers high, the shell tends to return to its pre-disturbed position.
Of course, you have meteorite impact perturbation.
Well, now what a meteor would do is just blow a hole in the thing. So one of the problems with the shell world is, well, it would take a long time for that to play out, even with a large hole. So the people living in a shell world would have to maintain an advanced civilization the entire time they're there to protect themselves.
And then one more quick thing.
Yeah,
I just wanted to
then
comment.
okay, great.
Since we talked about habitable zones, but I don't think anybody yet has mentioned today, you don't have to be within a certain proximity to a star to be in a habitable zone. A planet could be giving off its own nuclear energy, and so you don't have to be anywhere near.
And that's the point of a shell world. You can live anywhere, including some places that the rest of the universe think ain't even worth living in. And if you're very shy and very paranoid, that's where you'd want to be, right?
Yeah, two comments. One, nitrogen is not a problem. You don't have to go to Titan. Got 1 billion or 1 trillion comets. All of them have lots of ammonia. So
Thank you. Great point.
You could use
Why
that.
don't we, okay.
After all, that's how Titan
Thank you.
got its ammonia. The
All right.
second thing is, if
He
this,
said nitrogen's not a problem because his comet's full of ammonia.
also, if this advanced civilization elects to remain in organic form, they can greatly extend their life expectancies by moving inward as they age until they're near zero G, much less stress on their heart when they're near the center. It's another thing.
Yeah, I skipped over the slide that said alternate forms of you, because each of these is a separate ecology, and you could have just completely different ways of life. John, and then that's all I have time for. John, and then Robert. Okay.
Are we done?
No.
Oh, okay. Let me couch the question this way. There are things I don't understand. We have an adiabatic lapse rate of the Earth's atmosphere. And so I know
that's what I meant by scale.
I know that if I go to a height of 50 kilometers, I can put a thin Kevlar membrane around our entire atmosphere.
You could.
And it'll be stable.
Yeah.
Same for Mars, it'll be higher,
Yeah.
same thing. And so any gravitating object will have that property, so why do you need all this mass up there to stabilize it? Why, it seems like...
Because, well, on Ceres, the lapse rate is rather small. I mean, Earth is very dense, right? So we have a really good lapse rate.
Right, I'm coming to that.
Yeah.
Okay, so you agree that on a large object, you can have a membrane and it'll be stable?
Right, but on a large object like Earth, you've already got an atmosphere, so what's the point?
Right.
Yeah.
Okay, now, on Ceres, why bother with building the shell? Why not just use the object itself, bore to the center of it, and start hollowing it out from the middle outward?
You could,
then you've got what you want anyway.
In fact, one of the things we thought about is, you know what termites do to trees? You know, all those tunnels and, you know, around, then they kill the tree by completely tunneling under the surface and kill it. You could take that approach to a shell world, but this is a way to build it in one shot. The other thing is, if you simply dumped air onto a body, well, if it's a small body, you're going to need 10,000 kilometers of air before you get air you can breathe down at the bottom.
Yeah.
Quick question?
I'll ask my little comment. the population that you can support in your shell world is going to be limited mostly by the heat that they need to generate in their civilization to start moving forward. So it'll generate a lot of heat, and that also means that you can't hide in these because they'll be radiating at 300K or something.
Okay, I'll cover, let's cover the hiding thing by email, because that's a big subject. But as for the heat, all these bodies in the outer solar system are pretty cold, and so for a number of millennia, you'll be surrounded by a great big heat sink. And then you start to worry. Okay.